Good morning, everyone. Today's lead code question is 3721, that is longest balance subarray 2. So in this question, we are given an array nums and we have to return the length of the longest balance subarray in this array. So what is a balance subarray? So a balance subarray is a subarray that has the in which the number of distinct even numbers is equal to the number of distinct odd numbers. That is, suppose if there are five distinct even numbers, then it should have five distinct odd numbers, right? So we have to return the length of the longest balance subarray. If you'll see the constraints is the array length can be up to 10 ki power 5. So what are the possible solutions we can do is either big O of n or big O of n log n, right? N square will be giving us TLE, and the other thing is nums of I can be up to 10 k power 5. So we have to think of some approach that will be that has the time complexity as either big O of n or big O of n log n, right? So let's see the intuition and the approach. So this problem is a hard problem and the solution will be lengthy, so please be patient and please keep watching. I am 100% sure that you will get the approach, right? So what we do is, in normal case what we can do is we can take all the subarrays of the array, right? All the subarrays, and then check those subarrays whether they are balanced or not by counting the number of odd and even elements in the subarrays. But in the time size is 10 ki power 5, and this will be big of n square solution, so we can't do that thing, right? So what we do is, instead of like directly comparing sets for every subarray, we have to track a balance value, right? And what we do is we'll be fixing the right boundary r. That is, suppose our subarray is from L to R, so we fix the value of R, and then we will be varying L and keep checking. And we have defined A of L, where what is A of L? So A of L store the number of distinct odd number in L to R minus distinct even in range L to R. So basically A of L stores the difference of count of odd numbers in the range from L to R and count of even numbers in range L to R. And suppose if A of L is equal to 0, that means the count of odd is equal to count of even numbers, right? And that means our subarray L to R is balanced, and in that case what will be our length? R minus L plus 1, that will be the length of the subarray, right? So now we will be using this intuition thing to formulate our approach. So as we have fixed our right boundary, now suppose we have to extend our right boundary, right? Then we get a new element x, right? Suppose earlier our subarray was from L to R, then we increase R by R plus 1, then we get a new element, and that element we are calling as x. So what are the two cases that are possible? The two cases are that either x is not present in the range L to R, right? Either this x, the new element, is not already present. Then what will happen? Then it will affect all the ranges from 0 to R. So suppose we have 2, 3, 4 and 5. Suppose we have already calculated up to this R. Now we have 5. So if you'll see the range from 0 to 3, now it has 2 even and 2 odd. So the answer has changed due to the coming of this 5, right? So this new element is affecting all the ranges from starting index, that is 0 up to R, right? So what we have to do is we have to update a, that we have to update a from 0 to r, and right, and even if our number is even, if our number is even, then we will be subtracting -1, we will be subtracting -1, else we will be adding 1 in a to all the indexes that are affected, right? What is the other case can be possible? So the other possible case can be that whatever number the new number is present at some index I, and where I is less than r, so then it will only affect ranges from I plus 1 to r. It will not affect from 0 to r as it has affected in the previous range, previous case, right? So before I plus 1 it is already present, so we will be updating a, or array a from I plus 1 to r only. So and again the same thing, if nums of I are is odd, then we'll be adding 1, else subtracting 1. So take this example, right? 3 2 4 5. So suppose we have calculated all the what we call subarrays from index 0 to index 3. Now suppose this new element 2. So suppose if I'll take from 0 to 1 2 3 4, 0 to 5, in that subarray 2 is already present. 2 was already present, so the coming of this element hasn't affected that, right? Then I calculated from 1 to 5. In 1 to 5 also 2 is already present, but 2 to 5, 2 was not present. 2 wasn't present earlier. Sorry, 2 wasn't present earlier, right? So this has affected the previous answer. Previously 4 comma 5 is balanced, but the arrival of 2 has make it disbalanced, right? So the coming of this 2 is affecting the subarray from the next index at which it was earlier present. Suppose it was earlier present at past index. So what will be our range that the new element will be affecting? So it will be affecting from past plus 1 to r. This range it will be affecting. So we have to update a in this range only, right? But in the previous case, if it was not present earlier, then it was affecting from 0 to r, right? I hope till now you get whatever I have explained you. So let's move ahead. So next what we have to do is, so once we update the range for the new element, right? New element has come, we update all the previous ranges. Now we have to find an index L which is smaller than r, where a of L is equal to 0. Means a of L is equal to 0 means count of odd is equal to count of even, and that means it is balanced, right? So for finding this, we will be, suppose we will be iterating from 0 to r and take that index, smallest index L, where a of L is equal to 0. Then what will be our answer? Our answer will be r minus L plus 1, right? For this current index r, we get our subarray length as r minus L plus 1, right? But if you have noticed, right, so if we'll be updating a and finding L, so it basically takes big of n time, right? But if we'll be taking big of n time, then n elements are present, and for every element it is taking big of n time, so it is n square, which is not feasible. So we have to optimize this updation and finding this index L where a of L is equal to 0. So how can we do it? So for that we will be using segment tree, as segment tree takes only log of n time in updating and log of n time in finding the L. So in that case, what will be our time complexity? N log n, and that is a feasible time complexity as per our constraints, right? So and we maintain all A of L values in a segment tree, so we can apply range updates. As you all know, segment tree works good for range updates and range queries, right? So that's why we have used this segment tree. So our range updates will be efficiently, and we will be quickly finding a left boundary where a of l is equal to 0 in segment tree in log of and time, right? So next thing is like how to use segment tree, how we will be implementing our array a using segment tree, how we will be implementing this, right? So as we have seen, when we move the right boundary, right, earlier we have fixed l to r. So when we move this right boundary, we get a new element which affects the whole range of a values, right? So we need some data structure which supports this fast range updates. That's why we have taken segment tree. And each segment tree nodes, what it stores, it stores the minimum and maximum value of a in its segment. So why we are storing minimum and a maximum? Suppose this is a segment tree node, so it will store minimum value and maximum value in the range. So suppose if 0 lies between min and max, then we know that there is a balance subarray exists in this segment, right? Then we know that balance segment. Suppose this is a bigger subarray, right? And so we know minimum is suppose -1, maximum is 1. So 0 is in between these two, right? So any subarray is there in between this bigger segment that is balanced, right? So that's why we are storing minimum and maximum. And I hope you know that in a segment tree, if the parent node is at index p, then its child node will be at index 2 into p and 2 into p plus 1, right? These are the nodes, these are the indexes of child nodes if the parent node is at index p. So 2p can also be written as this one, right shift of p, right? This bit mask bits. And 2p plus 1 can be written as right shift of p by 1 bit and then or with 1, right? This is 2p plus 1. So these are the child indexes. So let's see. So what we do is what so when we get a new element, right, we see the above two cases. That is case 1, that are the new element is already present or not, and if it is present, and if it is not present, then we'll be checking the range that we need to update, right? Let's say the range can be ql to qr. So suppose we are at node p, suppose this is our node p, that is handling from range l to range r, right? Range l to range r. And our this new range is ql to qr, the range that is affected due to the coming of the new element, that is ql to qr. So we have to update this range. So we will be checking what are the different cases for this node p. See, there is no overlapping between our affected node, our affected range, and this range. In that case, we will be doing nothing. We will just go back. What is the other case possible? So the other case can be this are affected range, that is ql to qr, and this range l to r, they totally overlap, right? So in this case we will be update values of our current node, this p. We will be updating values of p, that is min value, max value of this p, and store the value. If store the value means +1 for odd number, -1 for negative number. And one more thing that we have optimized here is we have another variable, that is lazy. So we'll be storing the value in this lazy also. So at this point, instead of updating its child also, we store that value in the lazy, so that we'll be updating it later. So that also makes our solution faster. I'll repeat it once again. So instead of updating the child also at the current time, what we do is we store the value in a lazy variable of this node p, and we will be updating the child variables later instead of updating every time, right? Instead of updating the child of p every time, we will update them later. So this makes our solution faster. So our node have three things. Our segment tree node have three things: minimum, maximum, and a lazy variable. This stores the value that will be used by the children's, right? And the what is the third case that can be possible with our affected range, that is ql to qr, and our current node range, that is l to r. What is the third case can be possible? Partial overlapping, right? So in case of partial overlapping, what we'll do is the first thing, first we will push the lazy value from the parent to children, right? Lazy value is the value present at the parent that should be updated through the children. So first we will be pushing that value so that it don't get outdated. Means we first update the children with the lazy value, and then we call the function to add the value to the children of p, that is 2p and 2p plus 1. And at the end, once we update the children's, then we will be updating our current node min and max also, because the children's has updated. So suppose p has these two children, so if they has updated, then the maybe due to these, the minimum and maximum of p also gets updated, so we'll be updating that, right? Once we have updated all the ranges for the new element, so suppose new element x, we have updated the affected range, then what we do is we need to find the l where a of l is equal to 0 in the range 0 to l to r, right? We have to find L. So for this also we have three possible cases. So our current so our current range, suppose this is our current range QL to QR, and we have a node P whose range is L to R. So this is a node P who is handling the elements from range L to R, and our current range is QL to QR. So again, what are the three possible cases? There is no overlapping. So if no overlapping, then we want to be finding a of L is equal to 0. Then in that case, we will be returning -1. Else, what is the second case? There is overlapping, but the minimum is greater than 0 or the maximum is smaller than 0. Means this range cannot contain 0. Means 0 is not possible in this range. So in that case also we will be returning -1. What is the third case? Overlapping is there. 0 is also possible, but only one node. Means leaf node. Leaf node means we get our answer, that is will be the smallest L, where we will be getting a of L is equal to 0. Means balanced subarray, right? If these three cases, none of these three cases has passed, means overlapping is no overlap. If this fails, means overlapping is there. This fails means 0 is also there. This fails means it is not leaf node, means it is some intermediate node, right? It is some intermediate nodes. Suppose this is the intermediate node. So in the case of intermediate node, what we'll be doing is first we'll be pushing the lazy whatever the lazy uh, value we have right now, we'll be pushing that lazy value to the children's and update their minimum and maximum. Okay, so when we check child for a o l is equal to 0, then the if lazy is not updated, then they may give us wrong answer. So we have to update the lazy first, and then what we do is we will check the left child for a of l is equal to 0. And suppose we don't get any answer from left child, then in that case we will be checking the right child of this node, right? And suppose we have checked all the we have checked all the nodes of the segment tree. So what we get some index. If that index is not, if the answer is not -1, means there is some L possible. For that A of L is equal to 0. So our final answer will be R minus L plus 1. That is, R is our current index that we have fixed. L is the index where A of L is equal to 0 and plus 1, an extra element, right? So let's see the code. So please be focused so that you get it properly. So we have made a structure of segment tree, and a structure of segment tree is basically a node that have three things: minimum, maximum, and a lazy. So this we are using so that we do not have to update the we do not have to update the child every time, right? So whenever we update parent, at that time we there is no need to update child at that time, right? We can update child at later time when the child gets affected. So for that we have used another variable lazy, right? Then we have made a vector of this node, right? Min, max, lazy. And then we have first function apply. So what apply function is doing, so suppose p is a node of type this, right? And we have given a value v. V can be either +1 if number is odd, or it is -1 if number is even. So what we have to do is, we'll be updating our minimum with plus v, maximum with plus v, and lazy with plus v. If apply is called, we are updating min, max, and lazy, right? The next function is push function. So what push functions does is, it push the lazy value to the children, right? So suppose now we need some values from these children. So whatever value present at p, the in the lazy, we have to pass to the children's, so that we get the correct answer, right? So what push does is, it checks whether the current node p is lazy is not equal to 0. If the p is lazy is not equal to 0, it will call the its child p right shift 1, that is 2 into p, and pass the lazy value. Similarly, it also calls the child 2 into p plus 1, and also pass the lazy value, and mark lazy of p as 0, right? Once the lazy value is passed to the children's, then the same apply function is called, right? So their minimum, maximum, and lazy gets updated, right? Next we have pull अरे यार next we have pull function. So what pull function does is, suppose we have a parent and children's, right? So if we have updated children's, means their minimum, maximum has changed. So due to their change in minimum, maximum, there are chances that their parents minimum, maximum also gets changed. So pull function is to uh, updates the minimum and maximum of parent by taking the value from the children. So see, here it is taking minimum value from child at 2p index and child at 2p plus 1 index, and take the overall minimum. Similarly for the maximum value, right? Then we have another function, that is up range add. So what this range add function does, so here you will see two functions of the same name. Why? So we have done here function overloading, right? So initially this function gets called where L is the range, L to R is the range that is affected due to a new, what we called a new element added, and v is the value. V can be either +1 for odd, -1 for even. So if L is greater than R, means the range is not possible. It is not possible that the L lower element can be greater than our bigger element. In that case, we'll be returning back directly. Else we'll be calling this function where we'll be passing the node. first node at index 1, and the range is from 0 to n minus 1. First node's range is from 0 to n minus 1, means the whole array, and our current element is affecting the range L to R, and value is V. So if we'll see this case is no overlap between the two ranges. That is the range of the node, that is range node is L to R, and our current elements affecting range is QL to QR. If there is no overlap, we will be just returning. And the second case is like fully overlapping. In case of fully overlapping, we directly update the value of the parent node and then return. If these two cases are no there, means partial overlapping. In case of partial overlapping, we first push the lazy value to the children, then find the mid value, and then find the children of the uh, current node, and then add the value to that node, and then at the end we will again pull the values back and update the minimum and maximum of the parent, right? This is the range add function. Now after updating the ranges, we have discussed that we have to find the L, where a of L is equal to 0, minimum L. So this function is for finding the leftmost 0. So in this we have passed the range, right? That's get affected. So we again call the initially we again call the node 1 with whose range is from 0 to n minus 1, and the affecting the range that we have to check is from ql to qr. So node p denotes initially node 1 affecting range L to R, and R range that we have to check is from ql to qr. So again, first case is no overlap, then return -1. If this is fails, means overlapping is there, but minimum is greater than 0 or maximum is less than 0, means this range can't contain, this current range can't contain 0. In that case also we will be returning -1. So if this also fails, means overlapping is there, 0 is containing, and L is equal to R, means only leaf node is there. So that means that is our answer. So we'll be returning L. Overlapping is there, uh, containing 0, and it is also not leaf node, means this fourth case. Then will we first push the lazy values to the children, find the children, and then check the left value, that left child, that whether the left child has some L, where a of L is equal to 0 or not. If it gives left is equal to -1, means there is no answer, no L, where L is a of L is equal to 0. If left is not equal to -1, means some answer is there, then we will be returning that answer. But if left child not give any answer, then we will be checking the right child, right? So this overall is the structure. Up to this point, we have the structure for the segment tree. Now this is our main function of the uh, question. So in the main function, what we are doing is taking the size, making a segment tree and unordered map. What this map will store is this will store the last index where the element was present previously, right? Then initially we make the answer as 0, and then we will fixing our right value R. Okay, we take the number, check previous is equal to -1 initially, find, check whether this number is present initially before this current R or not, right? If it is present, then what will be, we will be updating our previous, then we will be checking whether this number is odd or even. If odd, then delta will be +1, if even, then delta will be -1, and then we will be updating the affected range. So what will be the affected range? Affected range is from previous +1 to R. So if it is not present earlier, then is from 0 to R. If it is present earlier, then the index at which it present +1 to R, right? Once we add the element, or we updated all the ranges that are affected, then we find the leftmost 0 from 0 to 0 to r, right? And if we get -1, if we do not get, if we get -1 means there is no l where a of l is equal to 0. If l naught is not equal to -1, then r minus l naught plus 1 is the length of the sub balanced subarray, and at the end will be the returning answer. So I hope I am able to explain you properly. So if you like the solution, please make sure to like, share and subscribe the channel. Thank you, and keep coding, keep growing. Thank you.